Welcome to the next session of the subject Engineering Maths. We were discussing chapter 3 concept limits and continuity, and the name of chapter 3 is calculus. Basically in calculus we have three modules. One is differential calculus. Differential calculus. The second chapter is, that is second module of calculus, is integral calculus. Integral calculus. And third category of calculus is vector calculus. Vector calculus. Now let us see. We have three categories of calculus: differential calculus, integral calculus, and vector calculus. Let us see what we discuss in case of differential calculus, integral calculus, and vector calculus. I give overview for a few minutes, and then we go for the first concept in calculus part, that is differential calculus. See, in the differential calculus, we can discuss limits, continuity of a function, differentiability of a function, maxima, minima of functions of single variable, maxima, minima of functions of two variables, mean value theorems, etc. Right? Now, in case of integral calculus, we discuss general integrals, integral a to b, f of x dx, some definite integrals, improper integrals, etc. In case of vector calculus, we will discuss line integrals, volume integrals, surface integrals by discussing divergence, curl of a vector, gradient of a field, directional derivative, etc. Right? See, when you look at this vector calculus part, this is the fundamental basic concept for electromagnetic fields and electromagnetic transmission lines for electrical and electronics and instrumentation students. Now, integral calculus, actually this is the fundamental base for probability and statistics class. Right? And even in the differential calculus, we can discuss many issues like derivatives, differentiability of a function, continuity of a function, mean value theorems, etc. All this differential calculus module is very powerful prerequisite for complex variables, numerical methods, Laplace transforms, etc. Right? So in particular, these two are very, very essential factors for Laplace transforms. Yes? And this is basic for electromagnetic fields and electromagnetic transmission lines. So this is the largest module in engineering maths, that is chapter 3 calculus. So it has three different modules: differential calculus, integral calculus, and vector calculus. Now in this session we discuss differential calculus, right? So we start with definition of epsilon neighborhood. Epsilon neighborhood. Let us see what it is. Suppose A is a general real number and epsilon is a number which is greater than 0. This is my general real number. A is a real number and epsilon is a number which is greater than 0. Since I am saying that this is a real number, this can be greater than 0, this can be less than 0, or this can be equal to 0 also. But we have a restriction on epsilon value, this must be greater than 0. Now in this case, when you consider this set, that is open interval a minus epsilon comma a plus epsilon, this is an open interval. Basically open interval is nothing but again a set. Now what will be the elements of this particular set? In this element, in this case, the elements will be like this. So whenever x belongs to this particular set, actually this is the symbol for belongs and this is the symbol for epsilon. So x belongs to open interval a minus epsilon comma a plus epsilon. That means all numbers above a minus epsilon and all real numbers below a plus epsilon belong to that particular set, and that we call it as epsilon neighborhood of A. When you consider x-axis, suppose A is located at this place. This is x-axis. A is located at this place. So this is a minus epsilon. This is a plus epsilon. A minus epsilon, a plus epsilon. Now therefore this open interval, this is called epsilon neighborhood of A. When you choose smallest epsilon, This can be neighborhood of A. I can take different values of epsilon so that I can produce many neighborhoods of A. So basically all these are neighborhoods of A. Let me tell you one simple example. Suppose I start with A value 2. Suppose A value is 2 and epsilon equal to zero point 0.1. Now its neighborhood is open interval 2 minus 0.1, that is 1.9. A plus epsilon, this is 2.1. This is called 0.1 neighborhood of A. Now basically it is a set having infinitely many real numbers. So how elements will be like this? Elements will be above 1.9 and below 2.1. So in case of set-wise notation, I can write it as set of x belong to R. This R represents real numbers such that 1.9 less than x less than 2.1. So this is my 0.1 neighborhood of 2. So basically interval is nothing but a set. All elements above 1.9 and all elements below 2.1. So this is called 0.1 neighborhood of 2. See, very simple. Generally, whenever your friends are there, whenever your neighbors are there, suppose your house is located at some particular place, right? My house is located at some particular place. If I assume that all houses are constructed in parallel, all houses are constructed in parallel. So my house is located at this place. So I will consider 50 houses on this side and 50 houses on this side. So therefore all these are called neighbors of myself. These are called neighbors of myself. So assume that all houses are constructed in sequential manner, parallel manner. So 50 houses on left side, my house is facing towards like this. So 50 houses on left side of myself, 50 houses on right side of myself. So basically in this neighborhood, my house is also included. So 50 houses on the right side of myself, 50 houses on the left side of myself, including my house itself. So how many neighbors are there? I am a neighbor of myself. So totally 101 houses are there. See, in case of real-time practical example, finitely many numbers will be there. But in case of real number system, we have infinitely many real numbers. So above 1.9, below 2.1, we have infinitely many real numbers. Therefore, when you consider any neighborhood of A, basically it is a set having infinitely many elements. That's why this is called epsilon neighborhood of A. Right? Suppose A is a real number, epsilon is a number which is greater than 0. Then open interval A minus epsilon comma A plus epsilon is called epsilon neighborhood of A. When you change frequently epsilon values, you can produce many neighborhoods for the same real number. Suppose if A is 2 and epsilon is 0.1, then this is the neighborhood of A. So what is the neighborhood? Set of all real numbers x such that 1.9 less than x less than 2.1. So basically every neighborhood of A is an infinite set, right? So note this point. Definition: epsilon neighborhood. Epsilon neighborhood. Let A be any real number. Let A be any real number and epsilon greater than 0. Let A be any real number and epsilon greater than 0. Then open interval A minus epsilon comma A plus epsilon. Open interval A minus epsilon comma A plus epsilon is called epsilon neighborhood of A. Open interval A minus epsilon comma A plus epsilon is called epsilon neighborhood of A. Example: A equal to 2, epsilon equal to 0.1. Therefore, its neighborhood is open interval 1.9 comma 2.1. Its neighborhood is open interval 1.9 comma 2.1. Open means here 1.9 is not included. 2.1 is not included. All real numbers between 1.9 and 2.1 are included. So write this set format. Set of all x belong to R such that 1.9 less than x less than 2.1. Next definition, absolute value or modulus. Absolute value or modulus. Suppose x is a real number. Actually, this R is nothing but set of real numbers. This capital R is nothing but set of real numbers. So when x is a real number, its absolute value is denoted by this modulus of x. Now it is a function which takes two different forms. So mod x equal to x if x is greater than or equal to 0, and this is minus x when x is less than 0. So mod x takes two different forms. When x is greater than or equal to 0, if it is a non-negative real number, then modulus is itself. If it is a negative number, multiply with minus to make it positive, right? So that's why whenever you discuss modulus of a real number, it is always a non-negative, greater than or equal to 0. Let us see an example. Modulus of 2 equal to 2, because this is a positive number. Modulus of 0 equal to 0. So if something is 0, its modulus is itself. If it is a positive number, its modulus is itself. Suppose if I take modulus of minus 2, since it is a negative number, it comes under second case. So make it positive by multiplying with minus sign. So this becomes minus of minus 2. Now this becomes plus 2. Now my question is, what modulus of a real number geometrically represents? See, whenever we have some concept, it has some geometrical interpretation, right? So like distance or something like that. Now let us see here. When you consider coordinate x-axis system, suppose this is origin and this is 2 and this one is minus 2. So here the distance between minus 2 and 0 is 2 units. The distance between 0 and 2 is again 2 units. And what is the distance of 0 from 0? That is itself. So therefore this 0 represents the distance of 0 from 0. This 2 represents distance of minus 2 from origin, and this 2 represents distance of 2 from origin. Therefore modulus of x always represents the distance of x from origin. This is the geometrical meaning, geometrical interpretation. So whenever x is a real number, its modulus always represents the distance of x from origin. Okay, note down these points. Let x be any real number. Let x be any real number. Then the absolute value of x. Then the absolute value of x is denoted and defined as. Then the absolute value of x is denoted and defined as mod x equal to x if x is greater than or equal to 0, minus x if x less than 0. Mod x equal to x if x greater than or equal to 0, minus x if x less than 0. Note down these examples. Note, the modulus of a real number, the modulus of a real number geometrically represents, the modulus of a real number geometrically represents the distance of it from origin, the distance of it from origin. Now let us discuss the concept of limit. So before discussing the concept of limits, let us discuss one important point on limit. Generally, when we want to calculate limits, for example, limit extends to 2x square, generally people will replace x by that number 2. But this may not be right in all situations, right? Suppose I want to calculate limit x tends to 2x square. Limit x tends to 2x square. So immediately people will replace x by 2. So in this case the result is 4. So practically this result is true in case of this particular example. But in all the cases, whenever you are finding limit x tends to 2 f of x, you are not supposed to replace x by 2. There are various issues. So before that, let us have definition of limit concept, and then we discuss various examples. In what situations x is replaced by this limit, in what situations x should not be replaced by this limit. Okay. So at first, let us focus on definition of a limit. Suppose f of x is a function and a comma l are two real numbers. Now I want to calculate this limit, that is limit x tends to a f of x. So we say that limit x tends to a f of x equal to L if for each epsilon greater than 0 there exists delta greater than 0. Of course this delta value depends on this epsilon value, so I write it as delta value depends on epsilon such that whenever modulus of x minus a less than epsilon implies modulus of f of x minus L less than delta. This is the basic definition of limit of a function at a particular real number. Let us recall this. We have a function f of x. A and L are two real numbers. They can be negative, positive, whatever it is. So we say that limit x tends to a f of x equal to L. Actually, what is my intention? I need to calculate limit of this function, limit of the function f of x at the point A. So my intention is to get this. So we say that limit x tends to a f of x equal to L. Here I am saying that x tends to a. What does it mean? X values are, here I am saying that x tends to a. That means x values are slowly approaching a. So when x is approaching a implies f of x is approaching L. That's the basic concept. But how to express mathematically? The mathematical version of limit of a function is like this. Let me explain how it is. It seems to be very complicated, but it is very simple. Let us simplify this. For each epsilon greater than 0, there exists delta greater than 0 such that whenever this happens, modulus of x minus a less than epsilon implies modulus of f of x minus L less than delta. So now our job is to what do you mean by this and what do you mean by this? Let us simplify this. Modulus of x minus a less than epsilon. Modulus of x minus a less than epsilon. Suppose I will take y equal to x minus a. Therefore, modulus of y is less than epsilon. But mod y is nothing but plus or minus y. According to definition of modulus, mod y is plus or minus y. So mod y is y or mod y can be minus y. So therefore, this is a combination of two inequalities, right? Now let us simplify this. So one case is y less than epsilon. This is one possible case because mod y is plus or minus y. So y less than epsilon comma minus y less than epsilon. But what is this y? X minus a. So therefore here x minus a less than epsilon implies x is less than epsilon a plus epsilon. So this is one inequality. Now when you come to this minus y less than epsilon, actually this implies y is greater than minus epsilon. So when you multiply an inequality with minus, less than becomes greater than and greater than becomes less than. So this implies what is y? X minus a greater than minus epsilon. This implies x is greater than a minus epsilon. Now you can see this equation, that is a modulus of x minus a less than implies, what does it mean? It is a combination of two inequalities. So x is less than epsilon and x is greater than a minus epsilon. So when you combine this and this, I will get this a minus epsilon less than a plus epsilon. A minus epsilon less than x less than a plus epsilon. This implies x belong to open interval a minus epsilon comma a plus epsilon. So basically what is this? This is a neighborhood of a. So when whenever x is in the neighborhood of a, then I will get this. So what is the meaning of this? Modulus of f of x minus L less than delta. It means that this means that f of x belong to open interval L minus delta comma L plus delta. So basically this is nothing but neighborhood of L. This is nothing but neighborhood of L. And this is nothing but neighborhood of A. This is nothing but neighborhood of A. Now let us come back to this. It's very simplified, almost simplified. So whenever x is in the neighborhood of A belongs, when is x is a neighborhood, the neighbor of A implies f of x is a neighbor of L. That means whenever x is very close to A, whenever x is very close to A implies f of x values are very close to L. See, very close is replaced by neighborhood in our mathematical language, right? So whenever x is in the neighborhood of A implies f of x is in the neighborhood of L. Therefore, because of these reasons, we can say that limit extends to A, f of x equal to L. Okay? So let me tell you one simple example. So I can recall many times also, but let us see. Suppose my function f of x is x square. So I want to calculate limit extends to 2x square. So it is a simple limit. So everyone has awareness about this. So this value is 4. Let us have a tabular representation. Suppose x values are like this: 1, 1.2, 1.4, for example 1.6, 1.82. Now these are my x values. The corresponding functional values are like this. See how I selected these values. This is my own choice. There is no logic, but I maintained one point, that is epsilon equal to 0.2. I maintained a distance of 0.2 for every consecutive real numbers. That's my own choice. You can take epsilon value 0.1, epsilon value 0.75, epsilon value 0.12. That is your own choice. So my interest is to take epsilon equal to 0.2. So when x is 1, 1.2, 1.4, 1.6, 1.82, the f of x values will be like this. This is 1 because f of x is x square. This is 1.44. This is 1.96, 2.56, 3.24, and this one is 4. Therefore, here as x values are approaching 2 implies f of x values are approaching 4. So because of this reason, we say that limit extends to 2x square equal to 4. So x values are reaching gradually 2. In that occasion, f of x values are gradually reaching 4. So because of that reason, we are saying that limit extends to 2x square equal to 4. Okay, right. So you please write this definition. At first, let me tell you. Let f of x be a function. Let f of x be a function and a comma L be any two real numbers. Let f of x be a function and a comma L be any two real numbers. And a comma L be any two real numbers. We say that limit extends to a f of x equal to L. We say that limit extends to a f of x equal to L if, now you continue this definition followed by this evaluation followed by this particular example. Hope you understand this. Now Let us discuss one important point on limits. Now earlier we have seen an example, limit extends to 2 x square equal to 4. Now in that case I have started x values from 1 onwards. So 1, 1.2, 1.4, 1.6, 1.8 like this. So what is my intention is I have approached 2 from left side of this. Even if I approach 2 from right side of this, if I get 4, then only I can confirm that limit extends to 2 x square equal to 4. Otherwise, I can't say that limit extends to 2 x square equal to 4. It is a very basic example, so everyone can say very easily limit extends to 2 x square equal to 4. But if you want to make sure that limit value exists and it's a finite value, then you must approach that 2 value either from left side as well as from right side. So in both the cases, if you are approaching to same value, if I approach 2 from left side, I approach 2 from right side. So in both the cases, if the function is approaching same value, then we can say that that limit is finite value and that is equal to that particular value. Okay. So the next concept is left hand and right hand limits. Left hand and right hand limits. Let us see. Suppose I want to calculate limit extends to a f of x. So I have two approaches. I can approach a from left side, or I can approach a from left side, or I can approach a from right side. So even in both the cases, if I get same value, I can say that limit value exists. Now let us see, the LHL is, this is left hand limit, and symbolically we write it as limit extends to a minus f of x. This is LHL, left hand limit. Limit extends to a minus f of x. Basically, a minus is not a number. It indicates that we are approaching a from left side of a. It represents that we are approaching a from left side of this. So let me write out this. Here extends to a minus means x value is less than a. Now my question is how to get this value. Just now I mentioned extends to a minus implies x is less than a. So what is f of x when x less than a? Simplify the function f of x when x is less than a. Once f of x is simplified when x less than a, replace x by the number a only. So you will get some finite value, right? Similarly, I can write RHL. This is right hand limits. So symbolically we write it as limit extends to a plus f of x. Now a plus, it means that we are approaching a from right side. So here extends to a plus implies x greater than a. Therefore this limit can be evaluated by replacing f of x when x is greater than a. How to get this? Simplify f of x when x is greater than a. Once f of x is simplified when x is greater than a, replace x by the number a only. Therefore my calculations are over. LHL calculation and RHL calculation is over. Now I will go for comparison of these two. Suppose if LHL equal to L, comma RHL equal to K, where L comma K are finite numbers, where L comma K are finite numbers, and L equal to K, then limit extends to a f of x exists. Limit extends to a f of x exists, and this limit must be equal to this common value. So limit extends to a f of x equal to L. So this is the basic concept behind the limits. I have calculated LHL. I have calculated RHL. Now compare both the limits. So I am approaching a from left side. I am getting some constant L. I am approaching a from right side. I am getting constant K. So if L comma K are finite numbers and L equal to K, this is very very important. L comma K are finite numbers and L equal to K. In that case, limit extends to a f of x exists. Exists means it's a finite number, and that limit value must be equal to common value, either L or K, because both are same. Okay. So this is the possible case to get limit value. So note these points. Now we discuss two important cases where limit is not possible. See here LHL value is L, RHL value is K. Suppose if LHL is L, RHL is K, where L comma K are finite numbers and L not equal to K. So this is one possible case. LHL value L, RHL value K, both are finite numbers. No issues till this moment. But the problem comes at this place. Here L is not equal to K. In that case, limit extends to A, f of x does not exist. Limit extends to A, f of x does not exist. So this is one possible case where limit value does not exist. LHL value L, RHL value K, where L comma K are finite numbers and L not equal to K. In that case, limit extends to A, f of x does not exist. Very simple. I am approaching from L. I'm approaching from left side. I am approaching from right side. So these two approaches will give two different values. Then how can you conclude that limit value exists? Which value I need to take? So I will be in a dilemma to take which value. Therefore, in that case, where L comma K are finite numbers and L not equal to K, then we can say that limit value does not exist. This is one possible case. Another possible case is if either LHL or RHL, if either LHL or RHL is not a finite number, then limit does not exist. So these are the two possible cases where limit value does not exist. Okay. So if I calculate LHL, I am getting indeterminate form. What are indeterminate forms? Sometimes I may get infinity power infinity. So it's not a finite number. 0 power 0. Generally people say that anything power 0 is 1. Anything power 0 is 1 means this is a finite real number except 0. So whenever you have forms like this, limit value does not exist. Sometimes you may get this also. So if either LHL or RHL is not a finite number, then limit does not exist. So note these 2 points. Note 1 and 2. Examples. First one. Suppose we have a function f of x defined like this. F of x equal to 2x plus 3. If x is greater than or equal to 4. X minus 9 if x is less than 4. Now when you look at this function, the domain of this function is set of real numbers. Here the domain is R. What do you mean by domain? For all real numbers, this function takes some finite value. From 4 onwards, the function takes 2x plus 3. Below 4, it is x minus 9. So for all real numbers, function has a meaning. From 4 onwards, it is 2x plus 3. Below 4, it is x minus 9. So for all real numbers, function is defined. So domain is R. Suppose I wish to calculate limit extends to 4 f of x. I wish to calculate limit extends to 4 f of x. Because before 4 we have one function, above 4 we have another function. So my task is to find limit at this boundary points. Now let us see, in this case I will go for evaluation of LHL. This is the limit extends to 4 minus f of x. So this is nothing but limit extends to 4. Here extends to 4 minus means x less than 4. When x less than 4, f of x is x minus 9. So therefore f of x is simplified when x is less than 4. Now since f of x is simplified when x is less than 4, replace x by 4. So this is 4 minus 9. This is minus 5. Now calculate RHL value. Here RHL equal to limit extends to 4 plus f of x. So therefore this is limit extends to 4. Extends to 4 plus means x greater than 4. Above 4 the function is 2x plus 3. Therefore f of x is simplified when x is greater than 4. Now replace x by 4. 2 into 4, 8 plus 3, it is 11. Now when you look at these two limits, this is a finite number L and this is a finite number, this is K. So as I mentioned earlier, LHL is a finite number, RHL is a finite number, but both are different numbers. Therefore, in this case, limit extends to A means 4. So in this case, limit extends to 4, f of x does not exist. Limit extends to 4, f of x does not exist. So write down this example. Now let us change some modification in this example. This is example 2. See, in this case, two left hand and right hand limits are giving different values. Now let us modify this function so that both will approach to same finite value, right? This is anyhow giving 11, but this is giving minus 5. So I will do some changes in this case. Suppose I can do directly like this. For example, this is a 3x minus 1. Now in this case, LHL left hand limit has been changed. So therefore limit extends to 4 minus f of x becomes 3x minus 1. Now when you replace x by 4, the value is 11. So this is 3 into 4, 12 minus 1, it is 11. Now in this case, anyhow this value is 11. So here LHL value is L, that is 11, or HL value K, that is 11. Both are finite numbers and same. Therefore in this case, LHL value or HL value both are same. So limit extends to 4, f of x does not exist, and this limit value is equal to 11. Now you can see when the function takes multiple forms, better to evaluate both LHL and RHL, right? When the function takes multiple forms means if the function is defined in more than one way, then better to evaluate both LHL and RHL, because in the previous example both are giving different values, but in this case both are giving same value, right? So to get confirmation, when the function has multiple forms, better to evaluate both LHL and RHL. Note down this example 2. Discuss example 3. That is evaluation of limit extends to 2 modulus of x minus 2 divided by x minus 2. Let us evaluate this. Limit extends to 2 mod of x minus 2 divided by x minus 2. What is my f of x? F of x is modulus of x minus 2 by x minus 2. So here also, as we seen earlier, modulus function takes two different forms. That means indirectly it seems to be a simple function, but it involves more than one function. So when the function has multiple forms, what we do? We need to go for evaluation of both LHL and RHL. Let us see. At first we calculate LHL value. So this LHL equal to limit extends to 2 minus f of x. So here x tends to 2 minus means x value is less than 2. When x is less than 2, x minus 2 is negative. Implies its modulus is, because this is a negative number, so its modulus is minus of this. Therefore the function is simplified. So when x tends to 2 minus, mod x minus 2 is minus of x minus 2. Anyhow, denominator part is simplified. Therefore this LHL equal to limit extends to 2. Now it is simplified, so in place of 2 minus you can write 2. So modulus of x minus 2 is minus of x minus 2. Therefore this is minus of x minus 2 by x minus 2. Now this value is minus 1. So it's a finite number. So to get confirmation, we need to calculate RHL also, because it's a finite number. So RHL equal to limit extends to 2 plus f of x. Here x tends to 2 plus means x value is greater than 2. When x is greater than 2, x minus 2 is positive. When x minus 2 is positive, its modulus is, it's a positive value, so its modulus is itself. Therefore RHL equal to, the numerator part is simplified. Mod x minus 2 is x minus 2. So therefore this is limit extends to 2, x minus 2 by denominator is anyhow x minus 2. Now it is plus 1. Therefore LHL value is minus 1, RHL value is plus 1. Both are finite numbers and they are different numbers. Therefore this particular limit does not exist. So the conclusion is since LHL is not equal to RHL implies limit extends to 2 f of x, that is modulus of x minus 2 by x minus 2 does not exist. Does not exist. So when you generalize this, here I have a number 2, this is 2, this is 2. So in general, I can do like this. Limit extends to p, if p is a general real number, modulus of x minus p by x minus p does not exist. So this is true for all real numbers p. So this is one important note. Limit extends to p, modulus of x minus p by x minus p does not exist. So basically this is a particular case of this. Okay, note down this example. Next example, let us modify example 3. I don't have denominator part, so f of x is mod x minus 2 only. I need to find out this. So in this case, I don't have x minus 2, so therefore this limit will be 0. Here also in the RHL we don't have denominator, this value will be 0. So both LHL and RHL are zeros. So therefore, since LHL, RHL both are same, so limit extends to 2 modulus of x minus 2. This value is 0. This value is 0. Therefore, even though function takes multiple forms, because of this modulus, we are getting LHL value, RHL value, both are finite numbers and both are 0, equal. So limit value is 0. Therefore, the conclusion is, whenever function takes multiple forms or function contains modulus, better to evaluate both LHL and RHL, because in the first case, function has two forms, limit does not exist. In the second case, function has two forms, but limit exists. In the third example, function contains modulus, limit does not exist. In the recent example, still even though function contains modulus, limit value is finite. Okay, note down this. You need not calculate entire, just to make note down this, limit extends to 2, modulus of x minus 2 is 0. The calculations you already understood, right?